what we really want to do with these ions is put them together and make ionic compounds, right? That's the interesting thing. All right, so an ionic compound is a kind of chemical compound that is formed when two ions interact. And specifically, what you have to have interacting is a cation and an anion. I should say and. Because cations with a positive charge are attracted to anions with a negative charge. And then that attraction is what holds them together, if that makes sense, right? So there's a couple things that we can pull away from this. One is that if you see polyatomic ions stuck together, then you can suspect that that's probably an ionic compound. But also, if you're looking up here at the periodic table, you see that the metals all make positive charges, and the nonmetals over here all make negative charges. So if you see a compound that combines a metal and a nonmetal, then you should suspect that that is a ionic compound. So for instance, if you put sodium together with chlorine, a compound that contains sodium and chlorine, knowing that sodium likes to make a +1 ion and chlorine likes to make a -1 ion, and so they would be opposites and they would attract, then you should suspect that. I think that's an ionic type compound. Does that make sense? Excellent. And then in addition to that, what you'll see is that, again, most of these polyatomic ions are negatively charged. There's a few, like ammonium here, has a positive charge. So if you see a metal with a polyatomic ion, knowing that they like to make positive charges, any metal atoms in a compound, you should suspect that it has an ionic type compound. So a metal plus a polyatomic ion. There, okay. There are some other types of ions that we're going to see in a minute, but before we do that, we just want to talk about how these ionic compounds come together and what the nature of that ionic bond is. So we can look at our sodium and our chlorine as elements that would like to lose or gain electrons. We can draw that as a equation. So if I did that, it might look something like this. And you could say, if we're looking at a chemical equation, our sodium atom would like to form a sodium ion and lose its electron. We can draw it like that. And our chlorine atom would like to gain an electron to form a chlorine ion. We can draw it like that. Does this notation make sense to you guys? Okay. Now the challenge that sodium has in making his sodium ion is that he can't just kick the electron out into the ether sphere and be like, see ya, buddy, I want to be charged, right? He can't just kick it out. It's still attracted. The electron is negatively charged. The sodium ion is positively charged. It'll still be attracted. It'll just fall right back in. So if sodium really wants to get rid of his electron, he has to find somebody to take it. And chlorine can't just find electrons sitting around outside on the ground, right? He's got to find somebody else who's willing to give it to him, right? So the equation, good question, Fatima, to say, what does this equation mean? This is showing basically what sodium wants to do. So we know that sodium has one valence electron, and if he loses that valence electron, then he'll have a positive charge, which is favorable. So we say the sodium ion would go to form, the sodium atom would go to form the sodium ion and lose one electron when it does that. And we can also say then the chlorine atom could gain one electron to form the chlorine ion. Does that make sense? So this arrow is to form, right? From reactants on the left to products on the right. Excellent. Okay. So this is what they like to do, but sodium has to find somebody to give its electron to. And this is what he'd like to do, but chlorine would like to find somebody to take an electron from, because electrons stay attached to atoms. They don't just hang out all by themselves. So you might look at it, and so in order for this to happen between sodium and chlorine, because it looks like they each have what the other person wants, right? Sodium has an electron he wants to give away. Chlorine wants an electron that somebody else is willing to give away. But in order for this to happen, they have to come in contact with one another. The sodium and the chlorine actually have to like see each other and touch each other for that handoff to occur, because again, sodium can't put that electron in the mail and send it to chlorine, right? You can't just stick it in the internet and email it, right? It has to meet up, right? So here's my analogy, right? Here's sodium sitting at home. And he looks around, he's like, I gotta get rid of this electron, I don't want it. So he goes on KSL, classifieds, and he makes a new post on KSL classifieds, 1 electron free, first come, first serve, come and get it, right? And chlorine, who's been looking for electron for a while, would really like an electron, and he's checking his phone looking for electrons on KSL because he's poor, so he's not going to be able to buy them for, expensive at the store. So he just is hoping somebody will give him one. And he sees sodium's post, and he goes, oh, wow, that's just around the corner from me. I've got a minute. I can go get it. So he messages sodium really quick. Do you still have that electron? I can come get it right now. And sodium says, yeah, sure, come on over. That's great. I've got it. Just first come, first serve. And so chlorine races over there and goes up and knocks on the door, and sodium opens the door and says, here's this electron, or whatever, if you like it, come take it. And chlorine is so excited, he grabs the electron, and at that moment, they look up into each other's eyes, and they're so attracted to one another. And now, years later, they still like to laugh about the day they met on KSL classifieds, because they were exchanging electrons together. Does that make sense? Did I lose you at the end there? Okay. They do the handoff, and sodium becomes positive and chlorine becomes negative, and all of a sudden, they're so attracted to one another. He didn't realize before how cute she was there in her pigtails. She didn't realize how handsome he was until that electron was handed off. But this is in part to illustrate what happens here when you make an ionic compound, right? So the ionic compound is formed when the electron is transferred from one atom to the other. And then the resulting ions are attracted to each other. So to show what happens, but also this interesting thing, the resulting ions are attracted to each other. That is the nature of the ionic bond. It is pure attraction. Positive charge attracted to a negative charge. So the sodium chloride ionic compound is best represented, potentially best represented, by showing we have a sodium ion and a chloride ion that are next to one another. And they're next to one another because those ions are attracted to one another. Now, the interesting thing about the ionic bond and the attraction there is that they're going to stay together until something more attractive comes along, because it's just attraction. And so I like to kind of call this like a high school relationship, because it's a very, very strong attractive force. Super strong attractive force. I mean, like the dramatic high school student who tells her mother, "Mom, you don't understand. You've never experienced love before." Because those hormones are just raging and overflowing, and you're just so attracted in ways you've never experienced in your life, and it's incredible, and you can't imagine that anything else could be better than this. And it's so strong, incredibly strong. And this is what holds together rocks, right? Rocks and the, like table salt. This is this type of compound. But if something more attractive comes along, they will split up. And so what this means for ionic compounds that are soluble in water, something really interesting happens. They will split up because the water overwhelms those attractive forces. So we can write this equation for solid sodium chloride. If I add it to water, it's going to split up. And this little S means solid, this little AQ means aqueous or dissolved in water. And when salt dissolves in water, it doesn't stay together. It completely splits up into individual ions, and it's called dissociation. Now, the reason that it does this, we're going to cover in a little bit more detail when we get to covalent compounds. But the short answer is the water molecules, which are covalently bonded, which is why we need this part of the equation. Water molecules have a bent shape. So they look a little bit like this. And I'm drawing bonds to indicate that there's a covalent bond, covalent interaction between the oxygen and the hydrogen. They're sharing electrons. It's different from the ionic bond, which is just attracted. These are sharing the electrons between them instead of having given them away. But the water is a little bit bent like this, and because of the properties of the atoms and the shape of the water, it ends up with a partial negative charge on this oxygen side and a partial positive charge on this hydrogen side, because each hydrogen has a partial positive charge. That's what that little delta means. And when you put salt in water, then the positively charged sodium ions are attracted to the partially negatively charged oxygens. And the negatively charged chlorine ions are attracted to the partially positively charged hydrogens in the water. Now, the one partial negative charge is never going to overwhelm the full negative charge here, right? So sodium is still more attracted to chloride here, the chlorine ion, than it is to that partial negative charge, except for the fact that if you're in water, you are surrounded by water. So sodium has like 100 of these partial negative charges just pulling at it until it just can't overcome that. So I'm going to draw these around here, these little water molecules as V's, right? Whereas the tip of it has the negative charges. So these are surrounding the positively charged sodium ion. And they're pointing towards it because they're attracted to it. And then for the chlorines, it's the opposite. It's the partially positive ends, the hydrogens, that are attracted. And again, those hydrogens are not more attractive to the chlorine than the sodium is. But when you've got 1 million of them, it's kind of hard to overcome. A decade ago or so, there was a show on TV. You know, reality TV, it's all terrible. And there was one that was more terrible, I think, than most. I shouldn't say that, I never watched it, but it was called Temptation Island. And you would take these couples who were engaged to be married, and you would put them on an island full of attractive young hotties and see how long that lasted. You can see why I say it's probably more terrible than most. But this is kind of how I feel that sodium chloride must feel when you dump it in water, right? Sodium and chloride have a relationship. They're strongly attracted to one another, and they've been together for a while. And so it's much more attractive, even if you put somebody else who's really hot next to them. They wouldn't automatically be like, oh, ditching you. But you can kind of overwhelm them, right? And pull them apart. And I always suspected that's probably what was going to happen with that particular show. Anyways, any questions? You do need to know that this process is called dissociation or dissociation. They dissociate in water. They disassociate from one another. They're no longer associated together. And that you do need to know that when you put an ionic compound in water and it dissociates to make ions, it becomes what we define to be an electrolyte. An electrolyte, by definition, conducts electricity. That's why it's called an electrolyte. It is the ions in the water that carries the electricity. So if you have pure water with no ions, it would not conduct electricity. But if you have water with ions in it, it'll definitely conduct electricity. That's why it's called an electrolyte. Now, you guys have heard the term electrolyte before, but not in this context, and you probably weren't given that definition specifically. Where have you guys heard that term before? Drinking electrolytes. Yeah, Gatorade, sports, Pedialyte. Yeah. Okay, so the reason that we drink electrolytes, either in sports or like Pedialyte, or if you like to drink Gatorade, that kind of thing, is the idea that when you work hard, when your body works hard, then it's going to sweat and you will lose electrolytes. And when they say you lose electrolytes, what we really mean is you're losing ions that your body needs, that you have in your blood. They come out as sweat. So you have salt in your sweat, you have other things in your sweat. And if you can take a drink that will replace the water and replace some of those ions that you've been losing, it'll be better for you, right? Whether you've been working out really hard or whether you are sick, there's another place you might need electrolytes. It can be beneficial to replace them, because if your electrolytes get out of balance, then you might experience uncomfortable muscle cramps, for instance. Now, most people with their typical workout probably don't need an electrolyte to recover. And in fact, you should know, because it's awesome, that one of the best post-workout drinks that you could find is chocolate milk. Have you guys heard that? Pickle juice. Sarah. I can totally see why somebody would say pickle juice, because I think it's got electrolytes in it. Definitely has salt in there. But yeah, so Ovaltine, chocolate milk, it's a good post-workout drink because it has a good balance of not just electrolytes, but also sugars to help you recover and some proteins and fats in there that will help with kind of like a long-term recovery. But really that's really just for like not marathon time, but like if you've been running for at least a half an hour or something, right? Not just like a little workout. So anyways, so chocolate milk is a good one, but that's where you might see electrolytes. And you might think that that's okay, not a big deal, but it's actually a really big deal. If any of you guys have experience in, for instance, the emergency room work, you'll find that a staggering number of people come in because they need electrolytes, right? If you get the stomach flu or gastroenteritis and you can't keep fluids down and you're dehydrated, you're going to come in and they're not just going to drop a bag of water on an IV drip. They're going to put saline there. They're going to replenish the electrolytes along with the water, right? Yeah, explosive diarrhea. I mean, listen, we're all here, potential healthcare workers. We can talk about explosive diarrhea, am I right? That's the kind of place where you would want to have electrolytes. In fact, you might consider, if you have gastroenteritis and explosive diarrhea, it's not the time where you want to be going to the store. So in terms of like emergency preparedness, I like to just keep a case of Powerade in my house at all times. So I don't have to go out and get it if I need it. Powerade, Gatorade, probably not the healthiest options, but they taste a lot better than Pedialyte. Also, just, from having been a mom for a while, I can tell you, get the white Mountain Blast color, because if you're prone to throwing up or your kids are prone to throwing up, you don't want that red color all over your carpet, right? So there's just a little hint or tip for you. Stock up on the white Powerade for emergencies. You can also have electrolytes in powdered form. And as David notes, you can store them that way. There's a recipe for oral rehydration therapy. You can just find it on Wikipedia. It's just a little bit of salt and a little bit of sugar, basically. And that can do it for you as well. Although I don't know that I don't know that it'll taste as good as Gatorade or Powerade, but just kind of a heads up there. So electrolyte gum, that's really interesting, Sarah. Sarah's seen electrolyte gum. That must be interesting. Now, salt pills, Nicole mentions there's salt pills that kind of do the same thing. Some people have advocated, well, you lose a lot of salt when you sweat, you should take pills, but you actually don't lose that much salt. And I believe that salt pills have generally shown to not work. In fact, I had a student, I think last semester, who was doing some long distance biking and got some salt pills just because he had ordered one thing and had a suggestion for salt pills. He's like, yeah, I've heard that this helps. He tried it. And he said that his sweat became so salty, like his body was trying to get rid of the excess salt. Like he'd never had it before, but it was like crusted on his eyebrows, if I recall correctly. It sounded terrible. But yeah, I mean, I've heard about salt pills too. Anyways, so according to the students who have tried it before, they say don't actually do those. You don't lose that much salt, and it's better to get it in your water as well. But some people swear by it. They're interesting. Note that you don't just lose salt, right? You have other electrolytes in your body, and that's why you'll see in Gatorade or Powerade, you'll also have magnesium, and you'll have potassium, and you'll have calcium, and some of these other ions that your body can use. So there's more to it than just that. But it gets that term electrolyte from the fact that it conducts electricity, which is why you as a person don't want to get struck by lightning or stick your finger in an electrical plug, because your blood is full of electrolytes and it will conduct electricity from the finger all the way across your heart or all the way down to your toes. So, and that's also why you don't want to be swimming in a swimming pool when there's a thunderstorm out, right? Because if the lightning hits the pool, that water will conduct electricity and electrocute you. Anyways, could also a good discussion here would be to talk about other diseases that cause diarrhea that would require electrolytes. So for instance, cholera as a great example that causes explosive diarrhea because you've got a bug that basically attaches itself to the inside of your intestines. And the problem with cholera is that you get it by drinking water that is contaminated. So the problem with oral rehydration therapy, which is like the only way to survive it, is you have to find a clean source of water, right? Because if you are drinking as much water as you can to replace the water that you're losing, it's got to be clean water. So, David, you're hilarious. David says he only swims in reverse osmosis or deionized water. The problem is as soon as you swim in it, then your body is releasing sweat and electrolytes into the water, and it has electrolytes in it. C. diff, there's another good example of obviously you'd see cholera in kind of third world countries or when you've got emergency situations. So you wouldn't see it as much here in the US, but certainly C. diff is something that you'll see in every hospital across the US as something that causes this kind of diarrhea, and you're going to need to do oral rehydration therapy in addition to trying to get rid of the C. diff or replace it, basically outcompete it with good bacteria there. Excellent. Okay, good. So that is the nature of the ionic bond. It's an attractive force. It's going to stay together until something more attractive comes along, which means it stays together for a very long time, except if you stick it in water, it will often separate like this and form this electrolyte kind of solution. Sarah says, does heat affect that? Does heat affect solubility? I think that's what you were talking about. Absolutely, it does. Things do become, generally speaking, things become more soluble in a higher temperature. So you can take some cold water and dump in salt until it stops dissolving. If you heat it up, you can dump in more salt and more will dissolve. But then if you cool it down, it'll start to crystallize out because it's no longer as soluble. Does that make sense? All right, here we go. So the next thing that we want to do is make ionic compounds. Now we have an idea of how elements might come together to make ionic compounds. We have an idea of the nature of the ionic bond. But in this class, we also want to know if I just give you a couple of ions and say, make me an ionic compound, what that's going to look like. So we're going to make ionic compounds. Oh, okay. So now the next thing we want to do is make ionic compounds. If I give you any group of ions, can you make an ionic compound for me? And there is one rule to making ionic compounds. Actually, there's a few, but there's one overarching rule that's very important, is that compounds are neutral. If I have a charge, I am still an ion. So if I'm going to make an ionic compound, I have to make sure there are no charges left over when I bring these charges together. So what I have to do then is look at, when I put a cation and an anion together, what is the charge on the cation? What is the charge on the anion? Excuse me. And then what is the lowest possible ratio of cations to anions to make a formula that has a net charge of 0? Because neutral means I have a net charge of 0. If I still have a charge, then I'm still an ion. That was our definition of ion that I gave at the very beginning here. Ions have charges, but compounds must be neutral. Okay, so if I'm putting my ions together, I've just got to make sure that those cancel out. So let's just say, for instance, I want to figure out what the formula is going to be between a compound that has a sodium with a positive charge and a chlorine that has a negative charge. And, oh geez, hang on. And you can see I've got a +1 and a -1. And so that's very easy. If I just have one of each, then those charges cancel. And I can get a formula that just has 1 sodium and 1 chlorine. And that is it. That should make sense. Now, convention says, you might notice here, the cation is listed first. And then the anion is listed second. So that's why I listed the Na before the Cl, and I didn't call it ClNa, okay? But 1 and 1, that cancels. Do you see how those charges cancel out? Like what would happen if, for instance, I put the sodium ion together with an oxygen ion? And remember, oxygen's in group 6, so it naturally is going to make a ion with a charge of -2, or 2-. What would be the appropriate formula that would give me the lowest possible ratio to make a formula with a charge of 0? What should I do there? Perfect. Nicole and Sarah both noted that I need 2 sodium ions. And if I put 2 sodium ions there, times that by 2, that'll give me 2+ overall charge contribution from the sodium. That'll cancel out the 2- from the oxygen. And so that will give me a formula that is totally neutral, has 0 net overall charge. So NaO, there's going to be a little subscript 2 there. So that's going to be Na2O. That would be my formula. Sorry, this is not super good for subscripts and superscript. Just like that. Does that make sense? Okay. What if I wanted to make a compound between magnesium, which is in group 2, so it's got a 2+ charge, and chlorine, which is in group 7, so it's got a -1 charge? Good. Perfect, Sarah Nicole. We're going to have 2 chlorines. Multiply that by 2. And then 2 times -1 gives me a -2 charge. that's going to be opposite the positive 2 charge from the magnesium, so those charges will cancel. So my formula here then is going to be MgCl2. And of course, when we're drawing the formula for a compound, numbers are going to be subscripts. Elena has a really good question. We'll get to that in just a second, Elena. I'm not ignoring you. We're going to build up to that, okay? All right. Note here in the formula for the ionic compound that I'm showing here, I never show the charge of the ion. I just say it's NaCl. And you know and I know that that's an ionic compound because I've got a metal sodium with a non-metal chlorine. And you know and I know that the charge on sodium is +1 because it's in the first column of the periodic table, and the charge on chlorine is -1 because it's on the 7th column in the periodic table. And so we don't actually write this as Na plus Cl minus. This indicates the kind of attraction, the kind of bonding that's going on. We're just interested in the formula here. So we don't show the charges, we just show the ratio, the number of each types of atoms that are involved. Does that make sense? What if I made a compound between magnesium 2+ and oxygen with 2-? Sarah and Erica, right on. Just MgO, because it's 2+ and 2-. They're equal and opposite, so they're just going to cancel out. So the lowest ratio is just going to be 1 of each. You wouldn't need like 2 of each or anything like that. Excellent. Okay. All right. What if, let's see, let's go to our periodic table here. What if we use these like +3s and -3s? What would happen then? What if I had, let's say, a sodium, which is +1 because it's in the first group, and a nitrogen, which is -3 or 3- because it's in the 5th column there. What would you do then? No, you just need 3 sodiums, right? We're going to multiply this by 3, because 3 times +1 is going to give you +3. That's going to cancel out the -3 over here. So you're just going to have Na, and we're going to put a little 3 down here, Na3N. You guys still with me? Does that make sense? Tricky to make that work. Okay. And then, all right, so what if I had magnesium, which is 2+, and I have nitrogen, which is 3-. Right, this one's tricky. Sarah's got it, but it's a little bit trickier because now it's not as obvious what exactly to do. You're going to use this thing that you learned like way back in high school or junior high math class called the lowest common multiple. And we see that between the number 2 and the number 3, the lowest common multiple, the lowest common number that is divisible by both of those is 6. So our goal is to make both of these worth 6. So if I multiply that magnesium 2+ times 3, that gives me a +6 charge. And then if I multiply thus nitrogen 3- by 2, that gives me a -6 charge. Then they cancel. And so as a result, you're going to get Mg3N2. 3 magnesiums, 2 nitrogens. Does that make sense? Now the 3 and the 2 are there because they make it so those charges cancel out. So when they're there, the overall charges cancel, but you still need to have these subscripts here to tell us how many of those you need for the charges to cancel. So overall, the lowest whole number ratio of magnesium to nitrogen ions is going to be 3:2. Now, there's a reason that they say the lowest possible ratio of cations to anions, and that's because ionic compounds don't make neat little molecules like this water molecule. It's a neat little self-contained bundle, an object, but that's not how these work, right? Because the sodium ion is attracted to the chloride ion, but on this side it's also attracted to another chlorine ion, and on this side it's attracted to another chlorine ion, right? Like any chlorines that can see it is going to be like, ooh, there's a positive charge, right? In all actuality, and now we're going into the z-axis, three-dimensional space, in all actuality the sodium ion is totally surrounded by chlorine ions. But then the chlorine ions, again, the same thing, that chlorine ion is attracted to sodium ions on all directions in three-dimensional space, and so on and so forth. So in reality, it's an extended network of attractive charges, right? So then this chlorine is attracted to that sodium, and so on and so forth. And there's this lattice network of chlorine and sodium ions. But we wouldn't want to say, yeah, this salt is made up of 1,000,000 sodiums and 1,000,000 chlorines, right? Instead, it is more instructive to say that on average, at the end of the day, if I break it down, what I find is the lowest ratio is that there's 1 sodium for every chlorine. Okay. Now, Elena asked a very good question. She says, can we use the crisscross method? So what the crisscross method is it forces a common multiple and just says you can easily find what the answer is going to be if I take the charge on one and I apply it to the subscript of the other, right? So if sodium is 1 plus and chlorine is 1 minus, I put a 1 from the sodium down to the chlorine, 1 from the chlorine down to the sodium, and I'm going to need 1 of each. And if you have sodium 1 plus and oxygen 2 minus, I can take that 2 from the charge on the oxygen and apply it down to the sodium. So I'm going to get 2 sodiums, 1 from the charge on the sodium. So I'm going to get 1 oxygen. And that works really well. I've got 1 and 1. That gives me 1 and 1. If there's 1, I don't have to show it. This is going to give me 2 and 1, and that's exactly what I've got. This would give me 1 on the magnesium from the chlorine and 2 on the chlorine from the magnesium. That works. And it's especially nice for something like this, where you've got like a 2 and a 3, just crisscross that, and that gives you the lowest, that gives you a common multiple. The challenge with the crisscross method is it doesn't always give you the lowest one, right? So if you used it on this guy, you might be tempted to say this should be Mg2O2. Do you see that? But Mg2O2 was not the lowest possible ratio. We can reduce that just to MgO. So be careful. The crisscross method is super convenient and easy to use, but every once in a while, it's gonna throw you off, right? So don't use it blindly as a rule. Just use it kind of as a helper there. Does that make sense? You guys with me? Here I can, this is a picture from the lecture notes that hopefully makes that crisscross method a little bit clearer, right? You take the 2 plus from the calcium, put it to the subscript of the nitrogen, and so on and so forth. And that would be the formula that gives you a charge of 0. Okay, excellent. Now, we can do this with main group ions like we've just done, and I think that that looks lovely. But we can also do this with polyatomic ions. These are another type of ion that we're going to be using. So we can make ionic compounds with these together or even with other elements. So if we do that up here, let's say, for instance, I'm making a compound between, let's say, sodium, which is a +1, and hydroxide, which is a -1, what would that formula look like? Just Na and OH, because you do 1 and 1. And again, we put the cation first and the anion second, right? What if we did, sodium, we'll do potassium, just for fun. I mean, it's the exact same charge, so it's gonna be the same kind of thing. And we put that together with our carbonate. Carbonate has a CO3 2-. What would that formula be? Right, Nicole, you're going to need 2 potassiums for every 1 carbonate for those to cancel out. So your formula is going to be K2CO3. And I'm going to put those back here. Does that make sense? Pretty similar, same. Okay, what if we did, magnesium, which has a 2+ charge because it's in group 2, and we did nitrate, which is the NO3 with a - charge. Perfect, Nicole. Exactly that. Right on, Sarah. You're gonna need, wait, no, back up. Both of you back up. Very carefully, because you're not the only one that might be making this mistake. I want to call this out. This is a formula of NO3, and the whole cluster of atoms, which includes 1 nitrogen and 3 oxygens, only contains a single -1 charge. It's very tempting to look at that as a 3-. That's an easy mistake to make. So be very careful of that. Everybody listening, pay attention to this, right? Having a 2+ charge or a 2- charge on a CO3 is different than having a structure of NO3 with just a 1- charge. Okay, so it's just a -1 and the 2+. Okay, so if we put this together, we're going to need 2 nitrates. But we run into a little problem because I can't say MgNO3 and have 2 of those, because then it looks like I've got 32 oxygens. Does that make sense? That doesn't work. So as Nicole and Danielle and Sarah noted, if you've been watching the notes, you'll know, what you have to do if you have more than 1 polyatomic ion to indicate that you have more than 1 of that whole cluster, so you're going to put it in parentheses to say this comes as a cluster and I have a certain number of this particular structure. So you're going to say MgNO3 and then a 2. So Mg, open parentheses, NO3, close parentheses, 2. And that tells you that there are 2 of those nitrates. It distributes through in just the same way that math would predict that it would using a parentheses. You have 2 nitrates, so it means you have 2 nitrogens and 6 oxygens. But that is different from saying I've got a compound. I mean, I could technically say MgN2O6, right? Because that's what it's saying in terms of how many of each of those elements that I have. But saying MgN2O6 doesn't tell me that the nitrogen and oxygen are held in this particular structure. And so we want to make sure that we keep that. So the correct way to do that is going to be not MgNO32 and not MgN206, but Mg with the parentheses and the nitrate in the middle, and then 2 at the end. Yeah, all these should be subscripts. Yeah, the N206 just looks wrong, sorry. This one, is this one clear though, David? That's just what it's supposed to look like to indicate, because we always use subscripts to indicate a number. A superscript on the right-hand side indicates a charge. You'll notice all of these charges are superscripts on the right-hand side. So make sure that when you're putting them together and indicating the number and type, that you're using those as subscripts. All right, so that is our introduction to making ionic compounds. And so I want to do a little bit of practice here before I let you go. So this is again from your worksheet, and I've got a little section where we're putting these together. So for each pair of ions below, what does the formula for the ionic compound look like? All right. So you guys tell me, what's it supposed to look like if I put Li plus and Cl minus together? Beauty. Sarah says LiCl. Perfect. I just need one of each. Okay, what if I put K plus and S2 minus together? What should that look like? K2S. Perfect. And I'm getting better at making these fake subscripts here. So K2S. All right. What about Mg2 plus and P3 minus? Mg3P2. Sarah, you were rocking this. I don't know if everybody else is with us and they're just content to let you answer all the questions, but you got it. Okay, now here we have 3 with polyatomic ions. No, you're fine. I am not calling you out. You're great. I'm calling everybody else out for not responding, for being lazy and letting you do all the work. HNO3. She is so fast. That's totally good. Okay, what about this one? Ba2 plus and OH minus. Excellent, Nicole. Perfect. And what about this one? NH4 plus. Ooh, 2 polyatomic ions together. Tricky, tricky. Excellent. NH4 2 CO3. Okay, so Nicole, how did you know that you needed to use parentheses on these last 2 questions? On some of these, the formula will look really funny if you don't, right? Like if you didn't, you'd end up with NH42, and you'd be like, wait a minute, there's something wrong there. But on some of these, it's not as clear, right? So BaOH2 might not look that weird. Yeah, so the reason that we use parentheses is because you needed multiples of an entire polyatomic ion. So since this comes as a bunch, and I needed 2 of them, 2 of that whole thing, not just 2 hydrogens, but 2 hydroxide ions, I can't do it that way, right? Now both of these come as a bunch, so why didn't I put both of those in parentheses? That's right. The carbonate isn't a multiple, so I don't need a parenthesis to say that I've got more than one of those. But the ammonium was a multiple, so I did need parentheses to indicate there was more than one of those. Excellent. Okay, so just to review on the last one, on the NH4, I've got a 1+ charge, and on the CO3, I have a 2- charge, right? So that indicates I'm going to need 2 times the +1 to cancel out the 1 minus 2. All right, so then when I want 2 times the plus 1, this plus 1 comes with this whole group of atoms because it's a polyatomic. So that's why I've got to put this one in the parentheses. And this minus 2 does apply to this whole bunch of atoms, but I only need one of them, right? So I don't need a parentheses 1 because we never put a 1 there, if that makes sense. And this 4 and this 3 from the NH4 and the CO3, they just come along for the ride, and they're not factoring into our math at all. Because when we're doing our math, we're looking only at the charges, right? I'm looking only at this plus 1, and I'm needing 2 of those. And I'm looking at this minus 2, and I'm going to need 1 of those. And the cross also still works on this one, right? So you get the 2 down here and the 1 down there. Does that make sense? All right, that one's tricky. That's all right. We can do some more practice problems here. In fact, this next section is kind of the same thing that we just did here, but we're going to take it a step, whoops. We're going to take it a step further. Move this all up here. Give myself a little more space. So this is the next section in the same worksheet. You're doing exactly the same thing. Whoops. That's not what I meant to do. Let's try this again. We're looking at section 4. You're doing exactly the same thing, except I'm making you take the extra step of identifying what the ion is. So I can give you the name of those atoms that are going to be forming the ions, or the name of those polyatomic ions, and then you have to go find what the ions are, including their charges, and then put them together, right? So here I gave you the ions and the charges and had you just put them together, but now we're taking this extra step. You know how to do this. Look at the periodic table, tell me what the symbol and charge on calcium is going to be, right? Let's try it. So I want you to do this. I do not want you to eyeball this and kind of rush ahead. I want you to do this in 3 steps, okay? Step 1. Oh, you know what? It's up here. What is the charge and the identity of the cation? What's the charge and the identity of the anion? And then look at the lowest possible ratio. So do it in pieces there. So let's look at this. What is calcium? Oh, Sarah's got it. Calcium's got a +2 charge and a symbol of Ca. So I'm looking at Ca with a +2. Good. And what is oxygen? It's symbol O and a charge of -2. Okay, so then I'm going to put them together and say the formula of the compound made between calcium and oxygen is going to have a formula of CaO, which is what Sarah said. Does that make sense? Step by step, we got this. Okay, let's do potassium and nitrogen. So what does the potassium ion look like? Perfect. Okay. Potassium and a single +1 charge. We can just say K+. What does the nitrogen ion look like? Perfect. It's got the symbol N. Watch out, capital N. And a charge of 3- or -3. All right, so what is the formula of the ionic compound made between potassium and nitrogen? What's that going to look like? Excellent. K3N. Perfect. All right. Ammonium and phosphate. So what does the ion ammonium look like? Not aluminum. Watch out. It sounds the same. Aluminum, ammonium. They sound really similar. The aluminum ion is Al with a 3+, but this is the ammonium ion. And I'll give you a hint. It's a polyatomic ion. So if you're looking at the periodic table like What the heck? I can't find it anywhere. That's why it's not on the periodic table. All right, David, awesome. NH4. What's the charge on it? No, it's not a minus. Plus. There we go. What does our phosphate ion look like here? Alexander, ammonium is one of our polyatomics. So it's in, I'm just going to scroll up here. It's in this chart that I copied over from your lecture notes. So it's this one right here. Yeah. While we're here, let's look for the phosphate because that's not an element either. It's polyatomic. There it is. Yeah, PO4 3- right here. Now, obviously, I just introduced these and I told you have to memorize them, but you don't have to have them memorized yet, right? So I'm happy to, if you're like, scroll up, I'm happy to do that. So it's PO4 with a 3- charge there. Okay. So what does the ionic compound made between ammonium and phosphate, what does it look like? Perfect. I'm going to need 3 NH4, so I have to put those in parentheses. NH4, 3, PO4. NH4, 3, PO4. Okay. What about hydrogen and sulfate? Good. Hydrogen's on the periodic table, and it's just a +1. Good. Sulfate. We're looking up here. Scroll up. I know they got it, but I wanted to scroll up anyway so everybody could have a chance to look at it, to find it here. It's right here, SO4 2-. Yeah, 2-. Okay. SO4 2-. Okay. So the compound made between these two ions is going to have what formula? H2SO4. Excellent. That's your sulfuric acid. Okay. All right. We've got 2 more minutes, so let's just finish these up and we'll be done with class for the day. Let's look at sodium and cyanide. Sodium is Na with a +1 charge. Good. Cyanide is Cn with a -1 charge. Excellent. And together, NaCN. Perfect. What about aluminum? Yeah. Al, the 3+ charge. 3 plus. And fluorine, F, the 1-. Perfect. So I put those together and I should get Al, F3. Perfect. Okay. Strontium and acetate. What does a strontium ion look like? It's SR, it's 2+, good. And what does the acetate anion look like? It's, yeah, one of our polyatomics, CH3COO-. Excellent. So what does that look like if I put them together? Good, I'm gonna need 2 of those acetates for every 1 strontium in order for that to cancel. Perfect. All right, magnesium, Mg plus 2, and nitrate. And NO3 with a -1. Okay, so if I put those together, what's it going to look like? Yeah, careful here, because I need 2 nitrates and it's a polyatomic. I still have to use my parentheses. Oops. 2. All right. Does this make sense to y'all? All right, so our lecture today is going to move from what we've talked about here, which is where we made ionic compounds, if we could identify the formula and charge of the ion, because we figured out how to put them together so that the overall charge would be 0, because if there's still a charge left, then it's still an ion. So what we're going to do today is start by going backwards and say, you know how this works. So if we end up encountering an ion that we don't know the charge of, we're not sure what it is, we can use what we know about ionic compounds to predict what that is, right? So here's how we're going to do it, predicting the charge in reverse. This is from your lecture notes. I've got 3 interesting ionic compounds here. And they're interesting and different in certain ways. So for the first 2, I want you to note we have some sort of an atom here that's not a main group element. Ag and Fe, if I scroll up to my periodic table as we were looking here, Ag is right here. It's a transition metal. We didn't do anything with transition metals. We only looked at main group, right? If you know the main group, then it's obvious what the charge is, but if it's transition, we don't know. And also Fe, right? Also a transition. So the reason that I didn't give you guys charges for these guys is that most of those atoms have available to them multiple oxidation states, which is a fancy way of saying they can choose to have different charges depending on what they're bound with and the circumstances of their ion formation. So sometimes in nature, iron will be a +3 ion. And sometimes in nature, iron will be a +2 ion. And sometimes even in the lab, you can make iron be a +1 ion. And so just telling you that you have an iron ion is not sufficient for you to know what the charge of that ion is. Unlike, say, magnesium. If you have a magnesium ion, then you just know, oh, hey, that ion is +2 because it's in group 2. Can't do that for iron. Can't do that for anything in the transition elements section there. Does that make sense? You guys with me? Okay. So there are a few exceptions that you can memorize. I'm not going to make you memorize them because I want to be consistent, but Mastering Chemistry will expect you to know that zinc is always +2 and silver is always +1. But otherwise, each of these, there's multiple options. And I should note, that's not just true of the transition elements, but it's also true of the post-transitional metals as well. Okay, so if you're in this party here, any one of these, tin or antimony, is graduated into this class. Okay, so we don't know the charge of that automatically. This option is really interesting because I've got a whole bunch of elements, and that's your clue that you have a polyatomic ion. Except that's not a polyatomic ion that you memorized, right? C6H5O7, let's scroll back up here. Not anywhere on this list do I see a C6H5O7. Now, this is a list of common polyatomic ions. This is not the list of all the polyatomic ions, okay? There's a million more, but these ones are common, right? I narrowed down a list of ones that you're gonna see in regular use. And so it's possible for you to see a polyatomic ion that you did not memorize. And so we're gonna use this method of predicting the charge and identity of ions in reverse, both for transition metal, for ionic compounds which contain transition metals, and for ionic compounds which contain these unfamiliar polyatomic ions. So for each of these compounds, to determine what the ions were that went into making it, you're going to follow these 3 steps. First of all, identify which is the cation, which is the anion. And the cations are always listed first, and methyl atoms always form cations. So for instance, with AgNO3, you're going to cut it right there and say Ag was my cation because it's a metal atom, and metal atoms always form cations. For this Fe2O3, we're going to cut it right here because Fe is a metal, and we know that metals always form cations. For this one right here, we're going to cut it right here because K, potassium, is a metal, and metals always form cations. Does that make sense? You guys with me? Okay, good. Then, step 2, do I know the typical charge of either a cation or the anion? I just need to know one, because if I know one, I can use it to deduce the other. So for instance, I've got silver here, which is a transition metal, and I have this NO3 here, which looks like it's got more than one atom, and that makes it a polyatomic ion, right? So do I know the charge? Right now, I did tell you that silver always has a particular charge, but because it's a transition metal, I told you I'm never going to test you on that. So I don't expect you to know the charge on silver, but I do expect you to know the charge on this because it's one of the ones you memorized. Any of you guys have those down yet? Started those flashcards? Which ion is this? What's its charge? It's the nitrate polyatomic ion. Excellent, Sarah. And it has a charge of -1. Good. Perfect. If nitrate has a charge of -1, and I know that this ionic compound, by definition, has to be neutral, and I only have one nitrate listed here, then what must the charge on that silver be in order to cancel out the charges? Perfect, Nicole. This is the silver ion with a charge of +1. Has to be +1 to cancel out the -1 from the nitrate. Does that make sense? We're going to be little detectives here, little ion detectives, and deduce. Okay, so for this one, we determined that the Fe atom was going to be the cation, and the oxygen is going to be the anion. And as far as typical charges, we don't know iron because it's a transition metal, but we should know the typical charge on oxygen. What should the charge on oxygen be as a main group ion? Nicole got it, -2. The oxygen ion has a charge of -2. Now this is tricky. There are 3 of them. 3 oxygen ions, each with a charge of -2, gives me a negative charge contribution of, Sarah said it, -6. I should say 3 oxygen ions times a -2 charge. -2 charge equals -6 overall. And so for this ionic compound to be totally balanced for charge, then the iron here has got to have a +6 overall charge. But there are 2 iron ions. So what should the charge on each iron be so that the overall charge is +6? You guys have got it. Perfect. So I could divide that by the number of ions there, 2, right? Because there's 2 irons. And that gives me information I need to know that the iron ion in this compound has a +3 charge. All right, there was another question here I want to make sure that I address. Erica says, will you always give us neutral compounds so they are equal? Yes, Erica, by definition, a compound is neutral. So if the compound is not neutral, then, or if the thing I'm giving you is not neutral, then it's not really a compound. And it would have to add up to the overall charge, but that would still be kind of weird. Okay, so for our purposes, it's going to be a neutral compound so that you can use this math to make it work. Good question. All right, let's do this guy. All right. Which species is the cation, which is the anion? I helped you pick that apart here because potassium is a metal. And then we want to know, what is the typical charge? Do we know either one of these two? Oh, sorry, Nicole wants to go back to the AgNO3 for a minute. The overall charge is 0 on the AgNO3. It must be because +1 minus 1 equals 0. Okay. All right. Sorry, Sarah. Do you know? Tell me, what do we know about this one? Typical charge of either one of these guys. Sarah says, we know that potassium, which is the K, has a charge of +1. That's our cation. All right. So, oh yes, there are 3 of them. Excellent observation. So now we have 3 potassiums times that +1 charge gives us an overall charge contribution of +3. That has to be canceled by whatever's over here as the anion. Okay, so what is over here as the anion? A lot of stuff. Yeah, a lot of stuff. Well, there's a lot of atoms there. But Sarah notes that what we have is C6H5O7. Pardon my lack of subscripts. I can't make that a subscript. Whatever that is. It obviously has got a name. Somebody knows it. We don't know it. We don't care. More importantly, we can identify that this is this cluster of atoms. So cluster of atoms with a charge must be some sort of polyatomic ion. What's the definition of that? Now, are there more than one of these so that we could like divide the charge by that like we did over here? Or is there just one thing? Sarah says no. How do we know that there's not more than one polyatomic ion there? Perfect. Sarah says there are no parentheses, right? If there was more than one of this polyatomic ion, then you'd have to have that in parentheses with some sort of subscript or something, and we don't have that. So since we don't have a subscript, then we know that that entire thing, whatever it is, must carry a charge, the whole charge to balance it out, of what? 3 minus or -3. Perfect. Potassium was +1, but I had 3 of them, so that +3 charge has to be balanced out by this polyatomic ion. I think I made that the citrate polyatomic ion. And there you have it, charge of -3, canceling that out. Does this make sense in theory? By that, I don't mean, do you feel like you're professionals at this? I just mean, Do you feel like you get the gist of it? Okay, because that's all we need to get us started, and we're just going to practice a lot more, and then we'll feel a lot more confident with this, okay? So I'm just going to go over to the ionic compounds worksheet again, and I'm going to paste these over here, and we're going to do a whole bunch for practice. You guys can help me here. All right, so again, three-step method. Which is the cation, which is the anion. Find which of those ions I know the charge of, and then use that to deduce the charge of the other one, because it's got to be neutral totally. Oh, I'm sorry, Zach had a question and I missed it. How did we come up with a -3? For this compound, we split it up right here because we noted that potassium is a metal, and metals always form cations, and they don't form polyatomics. So I knew not to break it here or there, right? It's very rare for a metal to make a polyatomic ion. If we look at our chart here, you do see there's one here in permanganate, and there's one over here in like chromate, dichromate, but it's really rare. I would not expect you to ever predict that, okay? So if you see a metal, you should always just cleave it off by itself and say, here's the positively charged ion that we're looking at. So potassium's in group 1, it always has a charge of +1, and there's 3 of them right here. So because there's 3 of them, we end up with 3 potassiums with a charge of +1 each, gives us a total overall charge of +3. So for this to be a neutral compound, the +3 has to cancel out with a -3 charge over on this side. So whatever's here has to have an overall -3 charge. And then because we determined there was just one thing, there wasn't more than one that would each have a different charge, then we said that one thing carries the entire -3 charge. So that when you combine the +3 and the -3 overall, it equals 0. That gives me a neutral compound. And that's through all of our ionic compounds, because they're compounds and not ions, they must be neutral. Does that answer your question, Zach? Oh yeah, no. The compounds will not have charges by definition, and that's the name of the game here. We're trying to figure out what must the charge on individual ions be so that the whole thing will not have a charge. Good, I'm glad we could clarify that. Okay, we've got space to leave that here. Okay, let's look at, I'm gonna go backwards just for fun. CrCl3. That's right, Erica. Sometimes we'll have to recognize that we have polyatomic ions, whether they are polyatomic ions we have memorized or not. So I'd like you to just know conceptually, here's what a polyatomic ion is, and be able to recognize one if you see it in the wild, right? If I hand you this compound and say, hey, what is it, right? Good questions. Okay, CrCl3, which is the cation and which is the anion? All right, Sarah says Cr is the cation and Cl is the anion. So there are only ever 2, just so you know it, just to make it simple. Ionic compounds have positively charged ions or cations attracted to negatively charged ions or anions. And you're never going to have more than 2 things, more than 2 ions in that ionic compound. All right, so we've got chromium is our cation, and then what's our anion then? The Cl is our anion. Good. Now, step 2, do we know the charge on either of those things? Yes, we know that the chlorine, because it's a main group ion, it's in group 7. Hang on, I'll scroll up here. I feel like I need to post another periodic table. Chlorine's right here, so it's in group 7. It will always be -1. We know that one. And looking on here, we'll find chromium's here. We wouldn't expect to just know that one because it's a transition metal. Okay. All right. So we know okay, scrolling down, here we go. So we know Chlorine has a charge of -1. Okay. All right. We know chlorine has a charge of -1, but there's 3 of them, right? So we have 3 chlorines, each with a charge of -1. That gives us an overall charge contribution of the chlorine ions of a -3. Perfect, yes. Which tells us, what does the overall charge contribution from our cations have to be? It's got to be +3. +3 on this side. Now, how many chromium atoms do I have? Just 1. So that 1 chromium has to have what charge on it? That 1 chromium has to carry the entire +3 charge. Perfect. Okay. That was all right. Should we do it again? You guys can let me know when you feel like you've done enough of these. All right, but this is kind of tricky, so I'm happy to do all of them. Let's do the FeO. Tell me, guys, what is the cation and what is the anion? Fe is the cation. Perfect. Yes. Fe is the cation. And what is the anion then? The oxygen is the anion. Good. Now, do we know the typical charge on either the O or the Fe? Ooh, what do we know about the O? It's got a 2- charge. So we've got oxygen -2. Now, how many oxygens do I have? Do I have more than 1 or just the 1? Whoa, whoa, whoa. I'm doing this FeO over here, right? Not this one over here. I'm doing this one right here. I only have 1 oxygen there, right? So I've got a -2 from the O. What does the Fe have to be to balance that out? It's got to be +2. Is that weird? Yes, it's weird. Yes, it's weird. Over here, iron was +3. And now you're telling me it's +2? Which one is it? They're both bounded to oxygen. What's happening here? Ah! The answer is iron is being iron. And sometimes it wants to be +2 and sometimes it wants to be +3. And you could just look at the compound and say, oh, today in this compound, iron is +2. Or another moment in a different compound, iron is +3. Okay, so you just have 2 different kinds of iron. And this is why we have to pick it apart and deduce what the charge is, because we can't just know, right? So that's what we get there. Okay, let's check out this guy. What is happening here? NaC7H5O2. Excellent. Sarah identifies Na is sodium. That's a metal. That's my cation. That's where I'm splitting that compound. And because Na is in group 1, it's got a +1 charge. Awesome. Sodium +1. Excellent. Which means, perfect, as Nicole identified, this guy over here, that's a polyatomic ion. And the charge has to be -1. It's a lot of atoms to carry just a -1 charge, but okay. Sounds fine. Looks good to me. Any questions on that one? Okay. Nicole wants to do CaH2, and that is a fair question. I was going to leave it for a minute because this one is tricky. But if we follow the rules, I think we'll be fine. So, which is the cation and which is the anion? Okay, the cation is always listed first, and metal atoms always form cations. So that tells you that the Ca is the cation and the H is the anion. Now, that should be a little uncomfortable to you. Why should that make you uncomfortable? because H is in group 1, and so that tells you that it like should be positive, you would think. Here, I'm tired of scrolling up, so I'm going to put a new periodic table down here. Okay, so this is tricky because calcium and hydrogen, you would look here and say, here's calcium. Okay, it's in group 2, so I know it ought to be +2. But here's hydrogen, which is in group 1, so it ought to be +1. But I can't have two cations, right? Two positively charged things are not going to attract one another. They just don't. Positively charged species only attract negatively charged species. So that's kind of interesting. Let's continue on here, see what we come up with, and then see if we can explain it, okay? So following this rule, because the calcium was listed first, I'm going to presume that it's the cation. And also because it's definitely a metal, whereas hydrogen is not actually a metal, right? It's sitting at the top of this column of alkali metals. But hydrogen is a non-metal. Remember, we talked a little bit about how it might fit here a little bit better because it's a gas, just like fluorine and chlorine. So that kind of makes sense. All right, so the H is what is confusing. What's the typical charge on calcium? Typical charge on calcium is 2+. So maybe we could use that to explain what's going on here. So calcium is a 2+ ion. And as we know, if I have one calcium with 2+ charge, I'm going to have an overall 2+ contribution. All right, which means over here, I've got to have what kind of charge contribution going on? It's got to be, if that's going to be neutral, that's going to be 2-. And how many hydrogen ions do I have? I've got 2. I mean, at this point we have a choice. We could either say maybe this is an H2 polyatomic ion with a 2- charge, but that would be weird. Or maybe we could say, all right, if it's just 2 individual hydrogen ions, then each of them would have a charge of -1. So then we would say, okay, hydrogen -1. All right, but that's weird because we like to think of hydrogen as being +1 because it's on top of that group 1 over here. Hydrogen likes to be +1 because if it loses the electron, it becomes a positive charge. Remember, electrons have negative charges. So if I lose an electron, it becomes positive. And so that's why he's here with lithium and sodium, potassium. They're all happy to lose electrons. Potassium will become just like argon because he's going to have 18 instead of 19 electrons. Sodium becomes just like neon because he has 10 instead of 11. Lithium empties that level 2 shell to go back to the full level 1 shell. And hydrogen empties the level 1 shell entirely and becomes basically just a proton. It's happy to do that. But what if it made a charge of -1? What would be the effect on hydrogen of becoming a -1 ion? Erica got it. If I gain an electron, that gives me a negative charge. That's weird. It doesn't really happen. Wouldn't predict it here. But everything in this column is happy to gain an electron because if they gain an electron, then they become like the next closest noble gas with a full shell. So hydrogen has 2 options. He can either lose an electron to be positive, have a completely empty shell, that gives him extra stability, or he can gain an electron to be negative, that gives him a completely full shell, also extra stability. We find that he more often loses an electron, but sometimes he can gain. We can explain that here, right? So if you see something that looks totally out of the wild, if you can explain it, then hopefully that'll help you feel more comfortable about that. But that's, again, I put this here because this is not something that you would have ever predicted. But given the formula and the rules for putting together ionic compounds, then you can deduce that that must be what is happening. Does that make sense? Okay, a little bit tricky. You guys let me know if you have further questions on that one. All right, let's do this calcium with this funky bromine thing. All right. Which is the cation, which is the anion? Calcium is the cation, perfect. And then this thing is the anion, and Zach notes that Ca is in the second column, so it's got a charge of +2 again. Okay. And so then if I look at this guy over here, it's got to have a negative. It's going to be kind of like we just did here, right? Total, it's got to be a -2 contribution. But there's 2 of them because we've got parentheses now. Which means that each of those BrO3 ions has a charge of -1. Excellent. What about TiO2? Ti is your cation. You guys are getting quicker at this. I'm impressed. Ooh, that was a terrible one. Okay. Titanium is the cation, and titanium being right here, we don't know a lot about it. Oxygen is the anion, and each oxygen has a charge of -2, which Sarah noted that there are 2 of them, which means that 2 oxygen ions multiplied by a -2 charge is going to give you an overall charge contribution of -4. That's what has to be canceled out over here. So here we have an overall charge contribution of +4. And how many titanium atoms do I have? Just the 1. So that 1 titanium, whoa, I can spell, has to have a charge of +4 all by himself. Whoa. You guys haven't seen a charge of +4 yet, have you? Like theoretically carbon could be + or -4, but we like never see that. That's a really high charge. But that's another thing that we see with these transition metals is that they can have charges that are much higher than you would see elsewhere. All right, let's move over here. What about AgCl? Ag is the cation, good. And the anion then is Cl, and which one do we know about? We know that the chlorine is -1 because it's in group 7, main group. All right, and so what would the charge on Ag be if I've just got one of each? Oh, you guys are good. Silver's just +1. So they'll cancel out. Excellent. SCN. What's my cation? What's my anion? Good. Sc is the cation. N is the anion. Which of these do we know a charge for? We know that nitrogen, being a main group ion, has a charge of -3. Good. Therefore, there's just one of each. The charge on scandium must be +3. Excellent. This is another one, scandium here, as a transition metal. You wouldn't necessarily know charge. All right, what about this guy? What's my cation? What's my anion? Go ahead. Sarah's got a question. Oh, good question. Do we write charges as +1 or 1+, +3 or 3+? It doesn't matter. Doesn't matter. It's all the same. Nicole noted that sodium's a cation. Which one of these do we know something about? Yeah, mastering it will be specific. So we know sodium. What is the charge on sodium? +1. Look, yeah, 1+. Doesn't matter. Good. All right, so what's going on over here then? Yeah, whatever this is, the ClO2, because it's a cluster of atoms, I know it's a polyatomic ion, it's got to have a charge of 1 minus or -1 so that it'll cancel out. Perfect. You guys are doing great. All right, almost done. Or do you feel confident about these, or do you want to do the last 3 here? Let's do one more. Good idea, Alexander. Okay, let's do OSO4. What's the cation? OS is the cation. That's a metal. What is that? Ooh. There we go. Osmium. Cool. All right, OS is a metal or cation, and the O is the anion. What do we know? We know that the oxygen has a charge of 2 minus. Good. But there's 4 of them, right? So what we have is 4 oxygen ions, each with a -2 charge. That's going to give us an overall charge contribution of a -8. Okay, well, how many osmiums do I have to split that charge between? Just 1. He is it. So the charge on osmium here is actually a +8. That is wild. That is so high. Right, +8 is about as high as you could go, but you can see +6 and +4s here as well. But that's really high. That's part of what makes this such a good oxidizing agent, toxic compound. All right, so that is actually the end of our ionic compounds, forming ionic compounds lecture. So let's take a 5-minute break, and then we'll come back and we'll jump into our naming ionic compounds lecture.